Hello everyone, welcome to Physics Rocks, it's true. Tonight's lesson is on magnets and electromagnets, and what we're going to take a look at is how magnets work, what a field around a magnet looks like, what a field even is. Then we're going to talk about electromagnets, how we can use electricity to make magnets and why that's a good thing. So let's get cracking. Okay, so when you look at a magnet, what you tend to get is a little rectangular object, and you have one end marked as north and one end marked as south. Okay, what we have are two poles of magnets. Be careful in exams, we see a lot of this as examiners, people talking about the positive end and the negative end of a magnet. This is not a thing. There is no positive end of a magnet, there is no negative end of a magnet. We have north and south poles. So please talk about poles when you're talking about magnets. When you label North Pole, what that means is if I was to hang this magnet up by a little string, it would swing around and the North Pole would point north and the South Pole would point to the south. We can use this to make compasses, but more importantly we can use compasses that we already have to label north and south on magnets that we haven't yet identified. And that's our first step here. So what we have is we have a magnet sat here. If I go and get myself a little compass, so let's draw myself one. So they're circular in shape with a little arrow in them. And it would be useful if I got an arrow. The arrow points north. More importantly, it points away from south. Okay, so if I was unable to identify the ends of my magnet, if I brought my compass over here, you'd end up with the arrow pointing away from this. And then if I brought it round here, it would be pointing towards the north. Okay, now we can use this feature to plot the field around a magnet. Now what we mean by a field is a region of space where an object experiences a force. Okay, so a magnetic field is a region of space where a magnetic object will experience a force. Okay, so this is important. This is true in basically all of physics. We have electric fields, we have gravitational fields, we have all sorts of things. So fields are basically regions of space where an object experiences a force. I pointed an S in there. There we go. So what we can do is fields are invisible, but they can be detected, which makes them super interesting. If I take my compass and I set it at the back end of my magnet, kind of like maybe here, and I get a pen, so let's grab a pen. What I want to do is I want to mark a little dot where the arrow points, and I probably want to mark a little dot at the back if I can get close enough there. Then if I lift my compass and I move it so that it sits on top of the dot, what you'll find is that the compass will start to drift in a different direction, so it'll look like that. And I just follow the same procedure. I put a little dot there, I put a little dot at the back if I can, and then I move it again, which becomes progressively more difficult. Set it on here, or even if you want to move it on a little bit further, but sitting it on top of the dot is usually the best way to do it. And what you'll find is that your compass moves its way around, and all you have to do is keep putting the dots. Keep doing that over and over and over and over and over again, and I'll get rid of my little compass here. And what you end up with is a series of dots that kind of make this type of shape here. Okay. Now sometimes that doesn't happen. Sometimes you make your dots and it just wanders off the edge of your page like this. And if you do it on the other end, you'll see that it's kind of symmetrical about these points. Now this is the fun bit where you get to play a game of join the dots, which is great fun when you've got a pen. Not the best of fun when you're clicking with a mouse on a computer, but we'll have a crack at it anyway. But all you have to do is join the dots up. Round and round and round and round and round like this. Join the dots. It's always good to do this one at a time rather than have your entire page filled with dots and then try and remember which dots were which. So join those dots up, join these dots up, and join these ones and do the other side. just like that. And there we have a basic simple diagram of what the field around a bar magnet sort of looks like. Okay. A little bit more detailed diagram of this looks much more like this. Alright, so it looks a bit like, I don't know, somebody squashed a spider on a page. So you end up with this series of lines, sort of like this. Pretty symmetrical looking pattern, one way or the other way. Now, the critical thing that you need to be able to do is you need to be able to add arrows to these lines. And in order to do that, you need to understand the convention. And our convention for arrows is that field lines flow out of north and into south. Okay, so up at this end, we want our field lines to flow out of north. And it's a really good idea to put the field lines near the actual north end of the magnet. That starts you off well. Okay, so these will be flowing out of north as well because they're still on the north side of the magnet. This one's also flowing out of north. And this one's flowing out of north. And this one's flowing out of north as well. And then they flow into south. Okay, so this one has that. This one is then flowing into south, into the south pole, and into the south pole. Now, the mistakes tend to come in this region here. So again, stay close to the magnet and go, right, there's an arrow there, and there's an arrow there going into south, and there's an arrow going into south, and there's one as well at the bottom. Okay, and now to do the middle end arrows, we go, right, well, it's coming up here and around here. So at this point, it's going this way. Same's true with this. Now watch this. Watch this. It's the same way on the bottom. A lot of people try to get some weird symmetry thing or balance stuff going on here, but no, they're all flowing out of north and into south. And this is the magnetic field around a bar magnet. And that's how it's done. You just set down a compass, go point to point to point to point to point, plot a point, move your compass, plot a point, move your compass, plot a point, move your compass, and then move it to a different start position. So to draw this diagram, you would have to start your compass, kind of here, 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 and so forth, all the way around. So everywhere it ends up touching the magnet, you would have to have had as a start point. But you need to do one side because it should wrap around. But if it doesn't, because you'll need these ones as well, you can come to the other side and you can get this whole set up here. Alright, now rules about field lines. This is important. Rule 1. The more densely packed they are, the stronger the magnet is. Okay, so that's 1. So if you've got a pile of them going on in the same space, then it's stronger than one that has less. 2, they never cross. Okay, if you've drawn field lines that run into each other, something's gone wrong. Okay, and the reason for that is that a field line shows you the direction of a force, the overall force that would be acting on an object in this field. You can't have an overall force that's moving in 2 separate directions. So if they're crossing, that's 2 ways that they can be drawn. So imagine I drew something like this. Okay, I had a field line coming here, like this. Well, if I put an object here, it can't have an overall force pushing it this way and an overall force pushing it that way. That's not an overall force. Okay, that's 2 individual forces that would make an overall force. So they can't cross by definition. So no crossing field lines. And number 3, as we've already discussed here, 3, they flow from north to south. Right. Simple. Right. Now, basic rules for magnets. I'm hoping that at the stage at your GCSE you probably know this, but let's make sure that we're right on this. Like poles repel. Okay, so north repels north, and by repel we mean pushes away. South repels south. Okay, and unlike poles, attract. Okay, so north attracts south. Right, and that's pretty cool. Magnets are awesome. They stick to stuff. They can lift magnetic materials like iron, steel, nickel, cobalt even. But their natural form ones have a little bit of a limitation, which is that they're always going to be sticky to stuff. They've got a set strength. We can't really use them on and off as if when we want them and when we don't. And this is where electromagnets come in. Okay, so what we need to get for an electromagnet is we need to get some form of core material. This is not entirely necessary, but it does massively help. Okay, so we need some form of core material, usually some form of cylindrical bar or something like that there, so core material. And the best core material to do with to use this is something called soft iron. Okay, soft iron is magnificent at magnifying the magnetic effect that you're about to get. And then all you need to do next is get yourself some insulated wire, so we'll draw it in green, and wrap it around your core material. Okay, over and over again. I'm going to do some very bad copying and pasting here. Alright, now that's not going to make you a magnet, but what we're then going to do is we're going to take these wires here and we're going to attach them to some form of power supply. DC power supply is best if you want to make a magnet that has a constant north and south pole. Later on in the course we'll not want that, we'll want to change that, but right now we're going to have a nice constant north and south pole. So we get ourselves a power pack, whack that in there. Now I've got a power pack, I've got electrons, and I've got current flowing all the way around this electromagnet, around this little coil of wire. Current comes out of positive, flows round, and flows up down the back, so you can't see what's going on down the back of this thing, but the current is flowing like this. Right, and this makes us an electromagnet. This end, this becomes attractive and sets it up as if it's a magnet. This end here will be north and this end here will be south. How do you know that? I hear you cry. And this is something called the right hand grip rule. So what I do with the right hand grip rule is I take my right hand like this and I grab on, or imagine grabbing on, to this soft iron core and my wires in such a way that my hand matches, or the direction of my fingers matches the direction of the current. I imagine that this flow of current is rolling up the back of my hand and over the back of my fingers where I can't see. Okay, so our current is going to flow up my hand like this, and then it's going to go onto my fingers, which I can't see, which is exactly what's happening in our bar. It goes up the front and then disappears down the back of them. If I stick my thumb out, then my thumb points to north. Right, so this is the right hand grip rule. If I switch my power supply around, so let's just do that. Grab that and switch around. Hopefully I can delete all these. I can. Okay, then what's happening is that my current again comes out of positive and heads this way. But this time it disappears up the back of the soft iron core, so I can't see that anymore, and then it appears up here and travels down the front like this. Okay, and each time it'll be appearing down like this. So to grab onto this with my right hand in such a way that the current is flowing over the back of my fingers and then around to the back again, I would have to grab it like this, upside down, which means that when I put my thumb out, we find north at this end. Right hand grip rule. Hard to beat. Okay, so why are we using these things? What's the crack with electromagnets? Why would we bother wasting electricity for something you can essentially dig out of the ground? Well, reason one is we just change our circuit ever so slightly, and in our wire here, what I'm going to do is I'm going to pop in a switch. Okay, so minor change to start with. So let's put a little switch in, like this, and finish this up. And this is like the most amazing thing. The most amazing thing there is going, that with the switch open, there's no electricity flowing around this. So this is now just a bit of iron with some wire wrapped around it. It's not a magnet. But the instant I shut this up and close this switch over, it becomes an electromagnet. This allows me to make magnetism that turns on and off. That's incredible. That is world changing. That allows you to build like disk drives. It allows you to lift cars. It allows you to make electric bells. It allows you to make circuit breakers for your house. This is incredible technology that involves a switch and some wire. Even better, if I get myself a variable power supply, so that is that I can change the amount of current that's traveling through this circuit, then I can affect the strength of this electromagnet. I can make this magnet stronger, and that's not something you can do with a regular magnet. You're stuck with strength from word go. Whereas this, I can up the power, I can make it stronger, I can lower the current, and that will make it weaker. Okay, so this will strengthen my magnet. Even better, if I'm kind of limited with my power supply, I have a maximum amount of it. If I stick more coils of wire on here, so there's more like kind of actually active coulombs in the circuit doing stuff for me, this also makes the magnet stronger. Right, so I can make my electromagnet stronger in 3 ways, and you need to know them. Number 1, I can increase the current. Number 2, I can add more coils of wire. And number 3, like we discussed at the start, we can use a soft iron core material. Because we can make this work with like a lump of wood, it's just not going to lift anything. It's not going to be strong enough. It'll turn a compass, absolutely, but it's not going to lift an object. Whereas use a soft iron core material, you can make these things so that they lift cars. Okay, well over a ton of material lifted with a magnet that you can then turn off and drop when you want it. Okay, the field around around an electromagnet looks exactly the same as the field around a bar magnet. It has a north pole, it has a south pole, and as a result, it has the exact same setup. Okay, so if I take my north pole and south pole diagram here, what I can do is I can just lift this electromagnet and pop it right on here, and it's the exact same thing. You get the exact same system, north to south, this kind of pattern. Okay, I hope this was useful for you. This gives you an idea that next time that we come around, we're going to look at how this is used in motors, how it's used in generators, and we're going to hit up the worksheet, which is linked below, and I'll see you in a couple of seconds to go over the answers with that. See you soon. Okay, welcome back. Worksheet question 1. If you haven't done the worksheet, hit pause, get it from the description below, at least have a think about these answers before watching this. But let's go. In the diagram below, draw the field around a bar magnet. You've got a north pole and a south pole, so you're essentially looking to reproduce this diagram here. You probably don't need as many lines as this, a good 6 will do. I'd recommend the straight line one out of north into south, then one each of these at the other end, and then at least one of these curvy inner bits. Alright, mark scheme for this, 3 marks. 1 mark for the general shape of it. 2nd mark for having the hours in the correct direction. 3rd mark is then for making sure the lines don't cross. So 1 mark, correct shape. 2nd mark is for north to south arrows with no contradictions. You make 1 mistake, the mark goes away. 3rd one then is they don't cross. Now the 3rd mark is going to be contingent on you getting the first 2. Alright, so if you draw a square that doesn't cross over, you've got the wrong shape and you haven't got arrows from north to south, so you don't get the 3rd mark for don't cross. So 3rd mark, you have to get the first 2 to have access to it. Question 2. Describe how to make an electromagnet. 2 marks here, so we're looking for 2 things. First thing, wrap coils of insulated wire around a core material. And if you want to be fancy, write soft iron. Though it doesn't have to be soft iron, you can make it with other things. That's your first mark. 2nd mark then is pass current through the wire. A lot of people forget that. But until you've got some electricity passing through there, it's not an electromagnet, it's just some form of weird sculpture. Number 3. Name 3 factors you could change to increase the strength of an electromagnet. Straight out of the video, straight out of your notes, this is a recall question. 1. More current. 2. More coils of wire. 3. Use a soft iron core. Try to remember using current here. You occasionally get away with voltage, depends on the examiner. Current is better here, so make sure you've got more current. And number 4, describe 2 characteristics of electromagnets that can make them more useful than permanent magnets. What we're looking for here is they can be turned on and off as needed. Okay, so what we're really doing is we're comparing and contrasting electromagnets to regular magnets. And number 2, the second thing that we want is that we can vary the strength of the electromagnet. And you don't have to use the word vary. You can put more current through it and make it stronger. Anything that gives you the idea that you can change the strength of the electromagnet. Right. Thank you very much for watching this evening. If you stayed to the end, really super well done. I'm hoping this is useful. Please drop me a comment below if this new format is working for you, or if you prefer to see the live stream stuff. It takes a bit more work for me to edit this, but I'm hoping it's a bit more useful. So if it's not useful, let me know. Hit the dislike button, leave me a comment. If it is useful, hit that thumbs up and let me know again what it is that you like about it. Is there anything I could improve? Right. Don't forget to like and subscribe. And until next time, don't forget, physics rocks. Oh, it's true.